Hi everyone. Okay, so this is part 2 of our ethers. We looked at heterolytic cleavage in part 1, so now we're going to be looking at our alpha cleavage. Don't forget our alpha cleavage is also known as our homolytic cleavage. So our difference here is going to be we will be moving one electron at a time. So I'm going to be using my fishhook arrows or my single barbed arrows with our fragmentation patterns. All right, just like I told you guys in that last video, the very first mass to charge ratio you should be looking at is the molecular ion. So I already have the molecular ion. It's already been ionized, and you got the cation. We saw that in our heterolytic cleavage where that was the mass of 116. That is the very first mass you should be looking for in that mass spec. So I'm just going to make that note here that the mass to charge ratio for this is 116. All right, watch video 1 if you want to see how we found that. All right, so let's get started with our alpha cleavage. So just like our heterolytic cleavage, there's going to be multiple ways to fragment this ether because it is not symmetric. Now, since we are moving one electron at a time, there's going to be a little bit going on here. For me, I always orientate myself by looking at where that radical is. That's always my starting point because that helps me organize my thoughts better. So that's what we're going to do to get started. So with this one, we're going to use that radical electron to begin the process of forming a double bond. And I'm going to try to form a double bond between oxygen and an alpha carbon. In this case, I specifically am going to fragment this bond, so that's why I'm moving it here. We are going to be looking at all the different ways we can make that double bond. So here I've started the process. Now a bond is composed of 2 electrons. I've only used 1 so far, so I need another electron to finish the double bond. I'm going to take an electron from this carbon-carbon bond. That will complete the double bond, but I still have 1 electron left in that bond. It needs to go somewhere. We're going to put it on the carbon right next to the alpha. And it's going to be the carbon that did not get the double bond, all right? It's not going to go way over here. That's way too far. So it's always going to go on the carbon connected to alpha, all right? So our fragments that we're forming here, well, I still have that methyl group on the left side. I now have a double bond to oxygen. Oxygen still has 1 lone pair, and then it still has this isopropyl group. So oxygen should have a positive charge. I've lost the carbons on the right side when I broke that bond. So now I have an ethyl group that's radical. Since the oxygen has the positive, that's the species I'm interested in for my mass to charge ratio. Excuse me. Now, we could go through and add all the masses together to get that mass to charge ratio. Not a problem. Will work just fine. Or I know I lost an ethyl group. So since I know the molecular ion peak, I could just say 116 minus the mass of ethyl. And I'm going to double check that because I'm never sure of anything. So 2 carbons plus I should have, what, 5 hydrogens? 29, that sounds right. So 116 minus 29, that should give me the mass at this fragment. Minus 29. Okay, so I should be getting 87. So we'll confirm that with our mass spec. Excuse me. Okay, so that's the first fragmentation. For the second one, hit pause and see if you get it. Try breaking this bond and see what you come up with. I'm going to go ahead and go. So again, I'm going to use that radical to start the process of forming a double bond. I will finish it by taking an electron from the sigma bond. That other electron in the sigma bond is going to go to the carbon bonded to the alpha. And our fragments that we're going to get here is this methyl group is what got kicked off. So that is forming my radical. So I have a methyl radical. Then I have formed a double bond with that alpha carbon. It still has that isopropyl group. We're going to have a positive charge. Yes, it still does have the lone pair. I don't have to show those. And then we do still have these 2 carbons on the end. So this will be the species my mass spec sees because it is the positive charge. Just like before, I know the mass of methyl. That's what was lost. So I can just say 116 minus methyl, which is going to be 15. So for this one, my mass to charge ratio of my fragment is going to be 101. So that is now my second alpha cleavage I would look for. And then I have 1 more fragmentation that I can do. So here, I'm now looking at this other alpha position. I've done all the alpha cleavages I possibly can for that lower one, so we are done with that. Now here, it does have two groups that are exactly the same. It has two methyl groups, so it does not matter which methyl group you choose to cleave, because you're going to get the exact same answer. I just happened to pick the one that was up here. It doesn't matter if you want to do that one, whatever makes you feel good inside, that will work just fine. But that also means I only have to do it once because I'm just going to get the same answer otherwise. All right, so go ahead, try to hit pause and see what you come up with. I'm going to go ahead and go. So again, I'm going to use that radical to get me started. So I'm starting the process of forming a double bond. I'll finish with the one electron from the sigma bond, and then I'll put the other electron in that sigma bond on that carbon. And so my fragments here is I'm going to have my sec butyl group here. This oxygen now has a double bond, and then I do still have that other methyl group. Yes, I have a lone pair. No, I don't have to draw it, but I will. And there's my cation. And then here, I once again am forming a methyl radical. Well, if I'm losing that methyl group again, my mass to charge ratio for this structure should be the same as before. Since I lost the same mass, I lost the same radical group as I did before. So again, you can go through and calculate it for yourself what the mass of this should be, but you should get 101. Okay, so that's all of the alpha cleavages I can do that are unique to this structure. So this is the same as before. So the masses I will be looking for are 101, 87, and then if we consider our heterolytic cleavage, we should have 43, 57, and then we are not going to forget about our molecular ion peak. So let's look at this mass spec. All right, so again, that first one I'm going to find is my largest, so that does line up with what I expected to see for my molecular ion peak here. Then I did expect to see 101 from my alpha cleavage. And then where was 87? 87 was also alpha cleavage. And then 57, let's see. 57 came from my heterolytic cleavage right here. And then 43 also came from my heterolytic cleavage. So I've been able to predict what peaks I should have. Now you do have this 41. We didn't expect to see that, but it's okay. We can explain that. So cations, specifically carbocations, this was for, I believe, our propyl group. Let me double check that. Yeah. So this was for our propyl group. Cations are weird because they can do a weird rearrangement where they're going to lose 2 hydrogens. So if you ever see a peak that's -2 from your cation peak like we do here, that's what that's from. It's not really relevant to the mass spec. Like I said, do not ever go through and try to assign every single peak in a mass spec. There are people who spend their entire careers trying to do that. You only need to interpret enough for you to figure out if it matches the compound you're expecting to see. All right, so that finishes up ethers. Hopefully that was helpful.